the simple thing is this. Obviously, I'm doing this for myself, and I am happy for me right now, and I just want to record a moment. I am gonna try to give you guys a glimpse of why am I so happy right now, and I am gonna explain it on a very simple way. Every element does not have, well, except the noble gases. Except the noble gases and certain atoms, certain molecules, which have bonded to fulfill the electron shells. Electron shells. But again, not every molecule and atom out there in the world has a filled electron shell. That's why simply corrosion on like steel occurs. I don't know how you pronounce that. I was wondering for like months already, how exactly do you calculate something called a reduction potential? A reduction potential, by now, it is a very well documented thing. In fact, I uploaded, a post on Instagram like a few hours ago, maybe, about just Wikipedia being kind of ridiculous with the amount of reduction words it's using. But again, it's a well documented thing. The reason why it is a well documented thing is because testing it's actually not that complicated. Testing reduction potentials uses something called voltammetry. Voltammetry requires you to have a difference in electrodes and measuring how much voltage difference it is going to have for your two given electrons in an electrolyte solution with a bridge for ions. And that we have done so many times for so many different compounds. Again, it is very well documented. But what it is not very well documented and is not very well understood, it's why, let's say, iron can have a reduction potential of a certain amount and lithium has a reduction potential of another amount. Both are atoms, both are made of electrons and neutrons and, just mass and energy. Why is it that some atoms have a different reduction potential than others? And that is very close to what today we are studying. It took me so many times of reading the stuff over and over again, misunderstanding and understanding again and learning by my mistakes to finally get to the point, and I finally got to the point today where I have a glimpse of an idea of why it happens. And the reason it's already been, in fact, I am going to talk a little bit about him. And this is the reason why. Can you see? Marcus theory. Marcus, it's a name. It's an old man by now. His full name is Rudolf A. Marcus, and he's 99 years old, so he's gonna die pretty soon. He's a grandpa right now. He made a theory. Well, his life work was done around the 1950s, if I understand correctly. 1950s, 1950 something, maybe 1960s. I'm not sure. I didn't really read the entire thing. I wasn't that interested. But he won the Nobel Prize on 1992. And what it says right here, I'm going to quote, is for his contribution to the theory of electron transfer reactions in chemical systems. Now, what does that mean, and why am I so happy that I read about it? And, I printed the thing and I read about it for like 2 days trying to understand the thing. By the way, the thing is so fucking complicated, it's insane. I have no fucking idea how the math on this thing works. It requires just so many different things that, yeah, I mean, I don't understand it right now completely, but it's the answer to why different atoms have different reduction potentials. And the simple way to put it is this: electrons moving around create chemical reactions. They create a difference in voltage. They create work to be done or work to be taken. For example, taken would be if a photon hits the electron fast enough, it is gonna move it around or heat up the atom or move the electron to a higher orbital state. And that is work done by the electron. The other way around is that an electron puts itself down and makes work available for everything else. Like, for example, to create a bond. Like, for example, to oxidize an agent. To be itself an oxidizing agent. Now, the reason why this electron moving around the orbital state and being shared with another atom or compound or whatever makes work and makes, in this case, my question, a reduction potential, is because these electrons move around, and the description of how and when they will move around, Grandpa did it, this old guy, and it is a diffusive. So again, I don't understand it correctly, but what I understand is this: it's a diffusion. It is not a very strong chemical bonding or action or movement. It is neither a nuclear interaction of the atom. It is, simply put, just an electron thing. The nuclei has almost nothing to do with it. But the electrons can diffuse, move around, and especially when another atom or agent is around, they can spontaneously switch places depending on the conditions. And this switching of places, it is, as far as I understand, very well described by his theory. And it theorizes when this happens, how much, and to a bigger extent, how fast and how I don't want to get this entirely wrong. How fast, depending on certain conditions, a redox reaction can happen. So his work not only describes how electrons diffuse and move around between orbital shells of different atoms, they also, by extent, theorize how fast and how often a certain reaction can happen on a given solution. And that's why I'm happy. That is his work, and I don't know how long it's gonna take me to fully understand it, but I am so happy right now that I finally, after weeks, months, I don't know by this point, like I don't know how long I've been fucking studying this, but yeah, I finally have just a tiny, minute understanding of why when an electron moves around different atoms, it creates a reduction potential. And hopefully it's not gonna take me that long to understand his work. But yeah, very interesting, very important person, obviously. You can look him up again. His name is Rudolf Arthur Marcus, and yeah, his work very important.